This is my implementation for our 6th programming assignment in the CST 370 course at CSU Monterey Bay. We were asked to provide a different implementation for the search function in the binary search tree. Previously it was implemented iteratively. We were asked to change it to a recursive search. So for the implementation that I did, I called an internal search method just so that I could pass the root of the binary search tree without altering its like private or public state. So I kind of added a new function. If you scroll down below, here is my implementation for the search recursively. All that happens is we pass in a node or a pointer to a node, and if it is not a node, we're saying that it is false and that the element that we're looking for does not exist in the tree. This is a base condition that will allow us to exit the loop if we get to the end of the tree and that element doesn't exist, or if the tree is empty. This search kind of searches each subtree. You'll see here. So here we're checking to see if the node that we're looking at is equivalent to the item that we're looking for. And if it is, then we return true. Down here is how the method is going through itself recursively. So if the item is less than the node that we're on, we know that it has to be in the left subtree if it exists. So here I'm grabbing the address of the root of the left subtree. And if it is not, then it is greater than, because it can't be equal to, because we covered that case up here. Then it has to be to the right of the element that we're on. So it would be in the right subtree. So we just call our search function again, which starts again at the top with the left or the right subtree. That's the basic implementation. So if you can imagine, if you're looking for an item, you would go to the root, and if it's not there, you would move into the left or right subtree, and then you would do that again and again until you either hit the end and it doesn't exist, or the node that you're on has the item that you're looking for. And then that would bubble up and return true from this function. The next item that we implemented was an in-order printing of the tree itself. In addition to printing the tree in order, we were asked to print it in the pre-order as well. I believe that these would both make more sense if we looked at a diagram of what is happening first. So here I have my example tree that I will show in the program later, with these values being inserted in this order. There are 8 values, and they create this binary search tree that is on the screen. So we insert 15 first, and 15 becomes our root. When we insert 20, we look at 15 and decide that 20 is larger than 15 and insert it to the right subtree of 15. We take 19, and 19 is greater than 15 and less than 20, so it is in the left subtree of 20. Then we take in 17 that we have up here, and we look at 15. It's greater than 15, and so we go into the right subtree. It's less than 20, so we go in the left subtree. Less than 19, and so it ends up being placed to the left subtree of 19. Then we take in 5 and look at 15. 5 is less than 15, so we insert it into the left subtree of 15. Then we take our next one, 1. It's less than 15 again, less than 5, and so it is set in the left subtree of 5. And then we come to our next value, which is 10. It's less than 15 and greater than 5, so we go into this right subtree of 5. And our last value is 30, so we go to 15. It's greater than 15, so we move into the right subtree. and that is 20 greater than 20, and it is placed in the right subtree of 20. So that's how we get the tree that I've created here. To go through the tree, both of the in-order and pre-order traversals follow the same path, and that is the path here. So both of them will prefer the left subtree of each node. So from 15 we'll go into the left subtree, which is 5, and then the left subtree of that, which is 1, and there are no more left subtrees, so we end up going back up to 5. And then to the right subtree, and then back up to 5, 15, go in the right subtree, and then prefer the left subtree again, and that continues. So that is the basic path of both of the algorithms. For the in-order traversal, I guess I should back up. The in-order and pre-order traversals, the only difference is really when the value is being printed. So the in-order traversal will climb down the left subtree as far as it can until it hits the end, and then it will print its value and then go through the right subtree. So we begin our implementation at this root node, which is 15, and immediately go down into the left subtree. We're not concerned about printing it yet because we have not finished our entire left subtree path. So we go down to 15, hit 5. 5 still has a left subtree, so we go down to 1, hit 1. 1 no longer has a left subtree, so that's when we print 1. Once we come back up to 5, we will have completed the left subtree, so we get to print 5. And then we go into the right subtree. And there is no left subtree, so we print 10. There's no right subtree, so we're going back up to 5, and then we get to go back up to 15, and the whole left subtree of 15 is complete, so we get to print 15. And then we move into our right subtree, and 20 has a left subtree, so we are not yet printing it, and going down to 19, and 19 still has a left subtree, so we go down to 17. 17 no longer has a left subtree, so we get to print 17, and there's no right subtree to go down, so there's no reason to continue on that one. And we move back up to 19, and we finally get to print it since its left subtree is complete. And up to 20, the same thing happens, and we get to print 20. 30, the same thing happens here. No left subtree, no right subtree, so we print 30, and then we get to go all the way back to 15, and then our algorithm is complete. So the note of when the value is printed is important. You also notice that all the values are printed in their sequential order, which is kind of neat. And so we'll move on to pre-order. As I said before, pre-order is following the same path as the in-order implementation. The only difference is when the values are printed. So in pre-order, the root or the node that we're on is always printed prior to traversing down the left subtree and before anything else happens. So in this case, we start with our root node and immediately print the value, and that is 15. Move down into our left subtree, print the value 5. Move down into our left subtree, print the value 1, and there's no left subtree, so we move back up to 5, and we have a right subtree, so we go into the right subtree. There is no left subtree, nothing else, we just print 10 and move on, and get to come back up to our root node and move into our right subtree of the root node, and the value is 20, so we just print that, and then move into the left subtree, print 19, left subtree, print 17, move back up to 20, and move into our right subtree of print 30. There is no left or right, so we don't have to do anything else here, and go all the way back up to our root node. That is a very simple description of what pre-order is doing. So we'll move back to our program over here and look at the implementation for in-order and pre-order. So this in-order case, which is the one where the value is printed after traversing the left subtree of the node, this case where we say the location pointer is equal to null, we just return early. That's just so we don't keep traversing down a tree that doesn't exist when we hit the last node in the tree. So once we get to that node, we just bump out. We don't print anything. We don't traverse anything. And that is our base case for this condition, or for this algorithm. Here we are doing the traversing. So once we hit once we're on a node, we attempt to go down the left subtree of that node. And this base case up here will break it out early and not do anything or print anything if that left subtree doesn't exist. And that's why this up here is here. After we've gone through the left subtree, here is how we will go through the and print the values of each node. After the value for each node is printed, we move to the right subtree. So, and we saw that in the diagram earlier. The pre-order implementation basically does the same thing, has the same condition for checking if the node itself does not exist, so that when we come down here and try and go left or right, we don't do anything when there is not a subtree. Here the only difference is that the data for that node is being printed prior to moving down the left subtree. And you can see the difference here between the in-order and pre-order implementations. The final piece of our assignment was counting nodes. We were asked to do it recursively. So, I guess I forgot to mention, for each of my methods, I followed the same path as I did before of writing a public function that calls a private function so that I could pass in my root and not make my root node public. So the tester application over here doesn't have to worry about, what the root is. That's all handled in the binary search tree algorithm, class. So back down to the node count. So here we are just recursively going through the tree and counting the nodes. It's a pretty simple implementation. We have the same kind of condition like we had in the pre-order and in-order functions, where here I just returned nothing. It's a void thing. Anyway, but here I had to return 0 so that nothing was counted, and that would break us out of the recursive chain. With this one, I'm basically adding 1 to whatever the count is for my left subtree and right subtree. The 1 is the node that we are currently on. So because that node exists, we have to add 1 to the count. And because these function calls call itself, we end up getting the total values in the tree because of this one. This one increments it in each of these cases. And then it will hit 0. So it's a pretty straightforward implementation. So I guess now we'll move on to actually seeing what this does. So here I'll have my program take the same values that I displayed in my tree that I created earlier. So we'll enter them in order. We have 15, 20, 19, 17, 5, 1, 10, and 30. Looks like they're all there, and end that tree. So we've just inserted all the values into our tree, and we should have this tree in our binary search tree class, or instance of our class. Here we are displaying the values in order, and you can see that they are in sequential order as we expected. And here they are in the same pre-order that we covered before. We can go back and look at my drawing. So we should have 15, 5, 1, 10, 20, 19, 17, and 30. And we have 15, 5, 1, 10, 20, 19, 17, and 30. So our pre-order function is working as expected. We count the number of nodes in the tree, and there are 8 as we had implemented here. 1, 2, 3, 4, 5, 6, 7, 8. We are good. And now we need to test the search function down here below. So we can enter in a bunch of values. I'm going to start by entering 0. And that is not found because that is not in the tree. Our very root was 15, so we could try 15. that was found. Let's see, over here we had, let's go back to this one. 1 was at the very left of the subtree, so that might be a fun one to test. Do 1, it is found. And then we have, let's do 17 and 30, or how about 19 and 30? So we have 19 found and 30 is found. So for some oddball functions, maybe we could try 19. That one should not be found. Oh, I'm sorry, that one is in the tree. So let's do 18. 18 is not in the tree, and we'll go outside of all of our values and try 31, and that is not found. So over here, I'll show you. We have 19 in the tree here, which I accidentally entered, and then I tried 18, and that would have probably fallen in here, and that was not there, so it was not found. Overall, our recursive search function is working, and that is the last of this program.